This is the first documented evidence of the strangest particle in physics. That particle being the neutrino. Even though that particle was discovered over 50 years ago, these particles are so elusive that we build enormous detectors. It's only with detectors like these that we can hope to detect the neutrino. The neutrino is so strange because it doesn't do a whole lot. Electrons, which are the cousins of neutrinos, are electrically charged, and so they repel and attract other electrically charged things. Quarks are electrically charged and color charged, so not only can they electrically attract and repel other things, but they can also bind together using the color force, quantum chromodynamics. But the neutrino doesn't have any of these charges. The only way that the neutrino knows how to interact with anything is via the weak nuclear force. And the thing about the weak nuclear force is that it only interacts with left-handed particles. Now, I made a video on left-handed and right-handedness and this notion of chirality earlier, so check that out if you're curious. But the basic gist is that left-handed particles transform in a counterclockwise way, whereas right-handed particles transform in a clockwise way, in a certain sense. Now, for the longest time, we thought that neutrinos didn't have any mass. Now, because neutrinos only interact via the weak nuclear force, and the weak nuclear force only interacts with left-handed particles, that means that we have no way of knowing if right-handed neutrinos even exist. But that wasn't a problem for the longest time, because we thought that neutrinos had no mass. And you can just have a left-handed particle without a right-handed pair if it doesn't need to have mass. So the standard model of particle physics just doesn't give neutrinos mass, and only left-handed neutrinos exist. There are no right-handed neutrinos. The trouble is, somewhat recently, we discovered that neutrinos have mass. And so the question is, how do they get that mass? You might say, well, they can just get that mass the same way that all of the other particles get their mass, via the Higgs mechanism. But that doesn't work so well, because the neutrino mass is so much smaller than the mass of any other particle, billions of times smaller, that it wouldn't be sensible to have a number that's so close to zero in there. The other thing that the Higgs mechanism would require is that a right-handed neutrino exists, but we've never detected such a thing. The alternative is that neutrinos are their own antiparticles, which makes them so-called Majorana fermions. If this really is the case, if neutrinos really are their own antiparticles, then you don't need the Higgs mechanism to explain why they have mass. But this introduces more problems. In the standard model, lepton number is the number of electrons, muons, tauons, and all the types of neutrinos, and that number is supposed to be conserved. But if you have a Majorana mass, well now, it's not conserved anymore. And that's a big problem. Let alone the fact that this implies the existence of a grand unified theory scale, which is a whole separate thing.